of what I hope you are thinking about when you're thinking about linear transformations. These are functions from one vector space to another. And of course, we usually call them v and w like this. And you're making a function. So I can draw that or visualize it as arrows pointing from the left side to the right side. And so there's inputs over here in v, there's outputs over here in w. And what the video was focused on are these areas in blue and red that I've put into this picture. The kernel of a linear transformation here, that's in blue, and those are the vectors in V that get transformed to zero, right? Now, of course, we learned the zero vector check a while ago, which said that, well, for a linear transformation, the zero vector of V must get transformed. Is that all over?
Yeah.
Thank you. The zero vector for V must get transformed to the zero vector for W, right? But there could be other vectors that also get transformed to zero besides just the zero vector alone. And we can gather all of those up into this so-called kernel of T, right? And that's this whole section in blue here. Those are the vectors in V that get transformed to zero, okay? Now, before I go any further, I mentioned in the video that this kernel of T always forms a subspace of V. And that is true. And I even did that as an example in the review session for the midterm. However, the review sessions is not required and not everybody saw that. So I would like to just put a little asterisk here. And I'm going to come over here and add this into our notes. Namely, that the kernel of T is a subspace of V. So again, some of you have already seen me explain this during the study session a week ago, but I just want to do it here so that everybody has it in their notes. All right. If I want to show that something is a subspace, I really have to do two things. I have to show that that space is closed under addition and closed under scalar multiplication. Okay, so let's talk about closure under addition first. All right, it's the usual two-step process. So closure under addition comes first. I have to pick two vectors that are in the kernel of T. Let me call them V1 and V2. So these are in the kernel of T. And in a minute, I'm going to add them together and make sure that when I look at V1 plus V2, the result is still in the kernel of T. Before I add them together, though, I just want to write down what it means that these vectors are in the kernel of T. This just means that if I transform them, I get the zero vector of W. So T of V1 is 0, and T of V2 is also 0. Okay, so that's what it actually means. And for those of you who just came in, we've got a handout here. Who else just came in? A whole bunch of people just walked in. Anybody else? Okay, that should be everybody. Great. Okay, so T of V1 is equal to 0 and T of V2 is equal to 0. So you can imagine that now I want to add V1 to V2 together, right? And I'm going to look at what happens when I transform V1 plus V2, right? This is the way I would set this up. And when I transform V1 plus V2, what do we know that we can do with this? T respects addition, right? So if it respects addition, then I can break this apart as T of V1 plus T of V2. And now I can plug in what both of those are equal to, right? They're both equal to 0. So this is literally just 0 plus 0, which is just 0. So there you go, 0 plus 0 is 0. And that means that V1 plus V2 is in the kernel of T, right? So let's just add that here. So V1 plus V2 is in the kernel of T. And you check that off. It checks. Okay, so that's closure under addition. Again, I'm just verifying that the kernel of T will always be a subspace of V. So I'm checking that it's closed under the two operations. Now the scalar multiplication, we also have to check this one. And just to set up the notation on that, I'm just going to let V1 be as above. And I'm going to come along and grab my scalar, which I usually like to call K. So K will be my scalar here. And I need to look at what happens when I do the scalar multiplication. So I'm going to take K times V1, and sorry guys, I'm going to use this bottom line here on my board. I think I can just squeeze it in. I'm going to take K times V1. I want to transform it and see if I get 0. So what's your knee-jerk reaction here? If I have T of K times V1, what can I do with it? Pull out the K, exactly. I'll pull out my constant. So K comes out in front. It becomes K times T of V1. This is because T respects scalar multiplication. And T of any vector V1 is just 0, right? T of V1 is equal to 0, so I'll plug that in. And when I take K times 0, of course, anything times 0 would just give me 0 again, which is what I would expect. And so K times V1 is also in the kernel of T. Excellent. So we check that off. And so this verifies that the kernel of T forms a subspace. Okay, so it's closed under addition and scalar multiplication. So of course it's going to have, the kernel of T is going to always have a basis and a dimension, and we can ask those types of questions. All right. Well, coming back over here again, so this blue part is now a subspace of V. That's the kernel of T. And to calculate the kernel of T, we're just going to be setting T of V equal to 0 and trying to solve for which vectors those would be. Which vectors get transformed to 0. It's really just solving an equation. It's really what it's going to come down to at the end of the day is you have to solve an equation. So far, so good? Questions yet? Okay, let's, if we're good on that part, let's talk about the red piece of the picture, which is on the W side of the diagram. You notice we have all these arrows that represent the function going from left to right, inputs to outputs. And not every single vector in W is necessarily going to receive an arrow coming into it. And the range of T, RNG of T, those are just those vectors in W that actually do receive arrows, at least one arrow coming into them. In other words, the red section here, guys, it's just those vectors in W that actually show up as outputs. Because not everything necessarily shows up as an output. So the range of T is just those parts of W that show up as outputs. And I mentioned in the video that the way to calculate that is to just take any basis for V that you want and transform all of those basis vectors and then form their span. Now, of course, when you take the span of anything, I was shocked. There were still a handful of people who got this wrong on the exam. There was a problem where the V was just the span of whatever, right? Anytime you take the span of anything, it is always a subspace. So this is a subspace of W guaranteed. I don't have to show anything, right? And I guess I can now add that this one, we just checked it, the kernel is a subspace of V. So these are both subspaces, yeah? And so the range of T looks like this. Now the vectors that are listed here, they may or may not be the basis for the range of T. It's always possible, guys. It's always possible that those vectors in that list could be LD, linearly dependent. So you saw me do this in the video. I take this list of vectors and I maybe have to remove the linear dependencies if I want to write down a basis. Yeah, so that does happen. That does happen. So what I'd like to do, guys, with you is review those examples from the video. I actually put them into this handout. It's got a front and a back side. So if you've got that close by, you might pull that up. There's in Canvas under the special handouts folder, I did put this document. So let me just see if I can actually blow this up nice and big and get it to a place where we can actually, let me maybe just download the thing here, where we can actually look at this nice and big. Let me get this out of the way. No, I don't need that. It always pops these things up. There we go. That's looking a little bit better. So this is the same handout that I just passed out, and hopefully it's readable to all of you guys. And I just want to talk through it. These are the examples that I did in those videos that you watched this weekend. So, you know, again, I give you in the box, I give you the formula for everything, right? So this first example, these should look familiar. I input vectors from R3 and I output a 2x2 matrix. And so I made up an example here that looks like that. Plug in A, B, C, and then output a 2x2 matrix, and I basically just made this up. So I just came up with some matrix here to spit out. And what you see that I've done, I've kind of split this into two columns, and I did the kernel on the left side, and I did the range on the right side. So to find the kernel of T, again, we don't need to take notes on this because you already did. I'm just kind of reviewing it. To find the kernel of T, you're just going to set the T of V equal to 0, right? So you set the transformation equal to 0, which really means that you're setting this matrix, which is the output of the transformation, equal to this 0 matrix. And you just slot by slot, you match up the four corners of the matrix, you end up just getting this one equation here, right? So A minus B plus C has to add up to 0. That's all you have. And it's a matter of solving that equation. It's only one equation, so solving it is a pretty direct process. I can just view this equation as having free variables B and C, right? So I call them R and T. And then if I solve for A, well, A is the leading variable, and it can be written in terms of those free variables as R minus T. Okay, you guys have done many of these kind of examples. So my kernel of T, if I just want to write down A, B, and C in terms of the free variables now, I can do that right here. And as always, to get my basis, I just have to bust out those variables. So you can see I get two basis vectors out of the whole thing. Okay, does that make sense? Did everybody follow that when they were watching me talk about it? Yeah, go ahead, Jose.
So the reason we only use A minus B plus C is because the negative of it is the bottom, right?
Yeah, this equation technically should have been there also. Negative A plus B minus C, setting that equal to 0, but it turns out that that's basically the same as this equation. So I just didn't write it down a second time. Yeah, good point. Other questions? So far, so good. Okay, great. What about the range of this transformation? Well, we've got in red over there, we've got the description of it. We simply take the span of a list of vectors. What is that list? That list is just the transformation of a bunch of things, and it could be any basis for V that you're transforming. There is no wrong answer to this. Pick any basis that you want, transform it, and you're good to go. Brian? There you go. So in this case, I chose the easiest basis for R3 that I know. You should always pick the easiest basis, right? Because it's the easiest one to plug in, right? T of 1, 0, 0, and then T of 0, 1, 0, and then T of 0, 0, 1. And I'm just going to transform each of those. Now, everybody has to be able, I've seen in the past where people sometimes have trouble like how to figure these things out. You're literally just putting in numbers for A's, B's, and C's here. So if I want to do T of 1, 0, 0, I'm just going to put a 1 for A, a 0 for B, and a 0 for C into the corners of this matrix and write down the result, which is right here. Pretty easy, yeah. For 0, 1, 0, I do the same thing, except I put the 1 where the B is, and I get this matrix right here. And then T of 0, 0, 1, I'm putting a 1 everywhere I see a C, and I get this matrix right here. Okay, just plugging it in, right? And what you notice is that these three matrices are not a basis for the range of T. And that's because, well, they are scalar multiples of each other. They're repeats. Actually, the third matrix is the same as the first one. And the second matrix is just the negative of the first one. Both of them are redundant. We would not want to spend $3,000 on this basis because two of the three basis vectors are just redundant of the first one. So we remove them. We just remove them, and then our basis is just the one remaining vector. It still sounds like we're reviewing chapter 4, right? It's still part of what we're talking about here. Yeah, so there you go. We have that. I want you to pay attention to this, guys. We have a two-dimensional kernel and a one-dimensional range on this example. Okay, so let's keep going because there's going to be some patterns that we're going to look for here. Is everybody good so far? Making sense? Okay, here's another example that was also in the video. This one is a little messier. So I have, this time I'm going to plug in a quadratic polynomial, and I'm going to spit out, again, a 2x2 matrix. So I'm plugging in, ax squared plus bx plus c, and I'm going to spit out a 2x2 matrix. And again, I just kind of made up these numbers over here, or these formulas here for the corners of the matrix in terms of A, B, and C. And again, to find the kernel of T, I'm going to go pretty quickly. Reviewing this again, to find the kernel, we just set it equal to 0. Now this time, all four corners of this matrix creates an equation for me. Setting each corner of the matrix equal to 0 creates four equations there that I have to think about solving. So it's going to end up in a matrix like it always does, right? So we end up with this matrix here, and I did not bring it all the way into row echelon form, but basically if you take the time to do the EROs here, you'll quickly find out that the C variable is free. The C variable turns out to be free, so I called it T. And then I just back substituted into this, basically into the first two rows to solve for B and then to solve for A. When you figure out what A, B, and C are, you do not want to put them into slots this time because my input vector space doesn't have slots. My input vector space is these quadratic polynomials. So you see what I really want to do is feed the A, B, and C into this form right here so that it actually looks like a quadratic polynomial here. Right, and as soon as I bust out that T, I get my basis vector. There's only one of them. There's only one basis vector because there was really only one free variable to bust out. That totally makes sense? Okay. The range of T, same kind of idea. Again, I have to take the span of a list of vectors. I chose the easiest basis that I know for P2 of R, which is just x squared, x, and 1. And I just hit each of those with T. So again, just be sure that you know how to actually evaluate these. Like, how do you calculate T of x squared from the general formula? Well, you just have to put in the right values for A, B, and C to do that, right? So if I want to evaluate T of x squared using this expression, right, I'm going to put a 1 for that A, and a 0 for the B, and a 0 for the C. And that's going to make this input look like x squared. So for T of x squared, I have to put a 1 for A, a 0 for B, and a 0 for C, and this is the matrix I get. Okay, and then I do the same thing for T of x using the B variable, and then the same thing for T of 1 by using the C variable. It's a list of vectors. But if I want to make sure that it's actually a basis for the range of T, I have to make sure that these vectors are not LT. And if they are, I have to throw away any vectors that were creating linear dependencies. So this is, again, just totally reviewing from chapter 4. If I have these vectors and I want to check if they're Li or LD, I'm gonna lay them into the columns of the matrix. Well, it just so happens to be this matrix again. So those vectors go into these columns, and sure enough, the third column ends up not having a pivot in it. I know I didn't do the EROs here, but that third column is going to equate with a free variable. Because of that, that third vector is creating a linear dependency. I've got to remove it. And then the basis is just the two vectors that are left. With me? This time, the kernel was one-dimensional and the range was two-dimensional. So keep that in mind. The dimensions of these things is kind of interesting. Let's flip the page over on the back side of the handout. The third example, is completely polynomial oriented. The inputs are polynomials and the outputs are also polynomials. The thing that's tricky with the third example is that the formula is given kind of abstractly. You notice that the input here, instead of writing it as ax cubed plus bx squared plus cx plus d, I just wrote it as p of x. I left it very abstract. And that's because the formula that I want to use could be written abstractly as well, you see. I can just do it, what does this say? 2 derivatives of p of x minus 3 times the derivative of p of x, whatever that is. Okay, so that's the formula that I'm giving you. And in order to really figure out the kernel and the range, we actually have to do the work ourselves of rewriting it using sort of the more spelled out notation. So I actually have to take this p of x, this p of x is living in the universe of p3 of r, right? That's my input. So I'm gonna write it actually in the form of a cubic polynomial here. So this is again what I did in the video. So just reviewing it, ax cubed plus bx squared plus cx plus d. Right. And I have to take 2 derivatives of that minus 3 times 1 derivative of that. Is that what I have there? You know what? On the handout, could you fix this for me? I lost the little prime on they just got cut off the Xerox at the very end of that line right there. There should be a derivative on that. I've got it right here on my slide, but then I Xeroxed this handout and I can see that I lost that derivative. Just on that one line, that's the only thing you need to fix. Everybody catch that? Otherwise you'll be confused later. Like, wait a minute, where's the derivative? It just got cut off, that's all. Okay, so anyhow, I take this cubic polynomial and I've got to take the derivatives of it. 2 derivatives here and then 1 derivative here. I just write out what that is. On the next line, I just rewrote it in the sort of the standard form of a polynomial. I put all the x squared parts in the front, all of the x parts next, and all the constant parts next. I just kind of gathered all of that up. And to find the kernel, right, I have to set this formula equal to 0. Now, when you're setting a polynomial equal to 0, what you're really doing, guys, is setting each of the coefficients equal to 0. So negative 9a should be 0. 6a minus 6b should be 0. And 2b minus 3c should be 0. And if you just look at this little system, I don't even really need a matrix for this one. It's pretty easy to figure out that A has to be 0 and therefore B has to be 0 and therefore C has to be 0. So they're all 0 except D, which is the constant term, never shows up in the right-hand side. So it's free to be anything it wants to be. I called it T. So the D is free. And other than that, all the other variables are 0. So if you look at your kernel of T, it's really just the constants. Actually, that should make sense. Which functions, which inputs would it be that when you take derivatives of them becomes 0? Well, anything that's a constant, if you took a derivative of a constant, you would get 0. See, that would not be surprising. It would not surprise me that a constant polynomial would be in the kernel. And as soon as I bust out that T, I get my basis. It's just 1. It's just 1. Okay. Sweet, and then the range of t, again, I just transformed the standard obvious basis for P3 of R, t of x cubed, t of x squared, t of x, and t of 1. I calculated all of those things by using, I could use this formula here, or I could just use the original formula in the box at the beginning. Either way, I'm gonna get these 4 results. Yeah. And obviously, if you get 0 in a basis, I shouldn't say obviously, but you never want to pay $1,000 for the 0 vector. This is never a vector that should be in a basis, so you get rid of that for sure. What about the others? Oh, they turn out, the other 3 vectors, if I just keep those 3, those do turn out to be Li. So we can keep those, and that makes our basis. So here's our basis, consisting of those 3 things. So far, so good? Questions? The last example is a quick one because it's an important one, but it's quick. This is the matrix transformation one that we spent a fair bit of time talking about last week. You plug in Rn, you spit out Rm, and you use a fixed matrix A to do it. And the size of A will be M by N. And in my video, I just explained that for this kind of transformation, when you're going from Rn to Rm, for any transformation like that, a matrix transformation, the kernel of T is just the null space of the matrix. Because you're just setting A times X equal to 0, which is literally the null space equation. So that's should look pretty familiar from how we described what the null space is. So the kernel of T is exactly the same thing as the null space of whatever the matrix is that's driving this transformation, that's creating this transformation. And the range of T, we can simply take the span of the transformation of these. I wrote E1, E2, and E3. Those are just the 1, 0, 0, 0, 1, 0, and 0, 0, 1, and so on. When you take the matrix A and apply it to those standard column vectors, you just get the columns of A. And I explained that in the video. So you're taking the span of the columns, i.e., otherwise known as the column space of A. So the range of T becomes the column space in this case. That's what happens. Okay. Questions on that, guys? I'd like to actually start making a little table here. So let's actually take some new notes now. I want to make sort of a summary of these examples. You've already got, obviously, the handout there, but this summary is going to be with some slightly different information in it. So like I'm going to, let's go back to the first example. This was a transformation from R3 to M2 of R. So actually what I'm going to do here is make a little chart again. So you might want to give yourself some space to make some columns. So this is the transformation. And what I'd like to do, sorry, I'm going to draw it like this if that's okay. I'm going to write down, I'd like to write down what is the dimension of the kernel of T, and then another column for the dimension of the range of T. And then later today, we're going to talk about something that will make even another column to this little picture. But let's just start with this. So for this first example, since you all have it in front of you, can you remind me for the example number 1, what is the dimension of the kernel and the dimension of the range?
2.
2 for the kernel. And what was the range?
1.
1, right? Does that look right to everybody? 2 and 1. Okay, let's go to the second example. So these numberings that I'm doing here are lining up with the handout. You're going to notice, by the way, I want you looking As I write these down, look for a pattern. I'm not just doing this for kicks, there is a reason for this. It's a pretty neat little thing we're gonna observe. Let's try another one, T number 2. T was going from P2 of R over to M2 of R again. That was the second example, and looking at the results there, what were the dimensions of the kernel and the range? 1 and 2, like so. Okay. Do you see any patterns yet? We have lots of examples, so we'll have time to figure this out. Let's look at the third one. The third one, T is a transformation from P3 of R going to P2 of R. And yeah, that's the one that's at the top of this handout here. Adrian, what is the dimension of the kernel and the range on number 3?
1 and 3.
1 for the kernel and 3 things in the range. Exactly right. This is a 1 and this is a 3. Anybody think they see any pattern yet? I will at least we'll make a general comment and then I'm going to take your idea.
Does it have to do with like the rank nullity theorem?
It absolutely does. Yes. Yes. Do you notice that when the kernel was big, the range seemed to be small? And when the kernel was small, the range seemed to be big. They're kind of working in opposite directions to each other. After all, the bigger this blue section is, right, the bigger the kernel is, that would mean more arrows are going to 0. That means the red part isn't going to be as big. But if the kernel is smaller, if the blue part is small, then the red part, that case, the red part becomes really, really big. Okay, in case anybody's in doubt, if you're not still quite sure you believe this, let's do example 4, because that's the ultimate winner to showing you how this works. On number 4, T is going to go from Rn to Rm, like that. And the dimension of the kernel. Does anybody remember what we call the dimension of the null space of a matrix? It's better known as the nullity of the matrix. Let's just put it into our table right here, guys. It's the nullity of the matrix. And what about the dimension of the column space of a matrix? What was that formula?
The rank.
The rank of A. Exactly right. And so this is sort of confirming Yakov's intuition that there's something to do with the rank nullity theorem here, guys. Right? The rank plus the nullity adds up to n. Right? Now, but look at these other examples. The dimension of the kernel plus the dimension of the range adds up to the dimension of V. Right? The dimension of P3 is 4. 1 plus 3 is 4. Check this one out. 1 plus 2, right? The kernel plus the range adds up to 3, right? Which is the dimension of P2 of R. Same thing on the first example, right? 1 plus 2 adds up to the dimension of Rn, which is 3. This is absolutely true. It's absolutely true. I'm going to ask you to leave space here for a couple more examples that we're going to add to this list in just a second. But before we do that, I want to write down the theorem that we are observing in this table already. It's a really, really cool result. Okay, so here is what I would like to call the general rank nullity theorem. The general rank nullity theorem, right? So here's what it basically is going to say. Let T going from V to W be linear. So we have a linear transformation from V to W. Then the dimension of the kernel of T plus the dimension of the range of T, if you add these two numbers up, it always adds up to the dimension of V. And of course, most of the time, you're gonna know the dimension of V off the top of your head. I imagine everybody knows the dimension of all these vector spaces off the top of their head. So if you know what the dimension of V is, then you have a way of sort of playing these numbers off of each other. They have to add up to that dimension. They have to add up to that dimension. Does that make sense? Yeah, so that's pretty nice. Notice, by the way, that W, the dimension of W has nothing to do with it. I think that there's a true false item on the homework for Thursday that puts W here instead of V. So I'll tell you right now, that's false. And the corrected version is to make sure that this is V right here. This is the dimension of V. Okay? Now, I want to express to you guys how incredibly important something like this could be. Let me come back here. I just love how math is sometimes. I just love this. Let me show you. Let's do example. I'm gonna go back up to example 3 in the handout. Oops. 3. Like that. Let's say for a minute that we did not know yet what the dimension of the range of T was on problem 3. And we came up with these 4 vectors here. Right? We actually know that this number does have to be 3 because of our theorem. Right? P3 of R is 4-dimensional. This is a 1. So we know that this is 3 even if we had not done anything with these 4 vectors yet. So actually, we know that these 4 vectors are LD without even taking a breath. It can't be the right number of vectors because the dimension of the range has to be 3, and I've got 4 things in this list. So you actually can determine that these vectors are LD just from the theory of the general rank nullity theorem, which is actually really pretty cool. Now, to be honest, this one's not that hard. You obviously are going to remove the 0. Actually, so let's say you remove the 0, because you never want to pay $1,000 for the 0 vector, and you have these 3 vectors left. Do I really have to check if they're Li? Not if I believe the theorem that I just hid from you behind this one, right? I know that the dimension of the range is 3. And I have, as soon as I remove 0, I have 3 vectors there. If they were LD, you would be throwing one of them away and your dimension would be going down below 3, which it can't. And this has to be a 3. Okay, so anyway, you can determine whether vectors are Li or LD just because of the knowing what the dimension of your space is supposed to be. I think that's pretty cool. Right, so anyway, it feels like Monday to me today, but that's because I was gone all weekend, so I'm kind of like, coming straight in, but I hope it's not affecting my energy and enthusiasm too much. I really do love this. I absolutely love it. Let me try and illustrate the power of this table by doing another example. So let's do a example 5 over here, maybe. I think I can get rid of this part for now. And we'll add a couple more examples to our list just so we can really feel comfortable about this. But yeah, this general rank nullity theorem, guys, let me get it up there for us, is super hugely important. Okay, we're going to use this a lot. So here is example 5. So I'm adding to my list of examples. I just want to practice. Let's define T from M2 of R to R via T of A, B, C, and D. So I'm going to plug in a 2x2 matrix, and I'm going to spit out a number. And the number I'm going to spit out is A plus 5D. I actually did this example at the start of chapter 6. So like it was the first example I did of linear transformations. And we know that it's linear from that, but let's actually take it a step further now and let's find bases for the kernel of T and the range of T. Now, normally I would start with the kernel and then do the range, but honestly, you can do them in either order. You can do them in either order, and when I come to my little table here, so on number 5, I'm going from M2 of R to R. If I figure out what one of these two numbers is, then I'll know what the other one is, because I have to add up to how much? Dimension of V, which is 4 for this example, right? M2 of R, sorry, I'm going fast. It's just 4. M2 of R is 4-dimensional. So we already know that the kernel and range have to have bases that add up to a total of dimension 4. Let's try to do, I guess I'll just start with the kernel. It doesn't really matter. So for the solution here, so for the kernel of T, just try this out. I'm just going to set T of A, B, C, D equal to 0. Which really just means that A plus 5D is equal to 0. So just using the given formula for the transformation. Now, if I look at this, this is just one equation to solve. I obviously can, if you want, you can think of it as a matrix with one row to it, a little system that has a single equation. Your unknowns are A, B, C, and D. Don't forget about the B and the C there. Those are 2 of the variables. This would be the matrix you would write down. And the point being that B, C, and D are all going to end up being free. The only leading variable is A, and I can write A, I'll just come over and do it on this side. A is just negative of 5D. And so my kernel of T, we can go straight into it, right? It's just going to be the matrices. Now let's make sure that we write the vectors in the kernel as vectors that are in the input vector space. Sometimes I see people draw 4 slots for A, B, C, and D, but this should be configured as a 2 by 2 because the domain, the inputs, the V vector space is M2 of R. But anyway, the A variable becomes negative 5D, the B is free, the C is free, and the D is free. So I'll just use B, C, and D here. I could change them to R, S, and T, but it's also fine to just leave them like this. This is such that such that B, C, and D are in the real numbers like that. Yeah. So there's your kernel of T. And let's bust out those variables to get our basis. So the basis here, we're just going to make our list. So we get our squiggly braces going, and the B variable is only in the top right corner, so we get 0, 1, 0, 0 for that one. And then the C variable, when I bust that one out, I get 0, 0, 1, 0. And the D variable, when I bust that out, I get negative 5, 0, 0, and 1. So that's going to be 3. That's going to be a 3-dimensional kernel. That all look okay? Sometimes I'll get people asking me, well, why don't you check that they're Li? I mean, after all, that would seem like a required step. And you're right, we could stop and check their Li, or we could do the range instead and take a look at what we get from that. So if I do the range and see, guys, so I actually am going to not check that these are Li directly. Instead, I'm going to do the range of T. Let's see if I can squeeze it in right here. Actually, there's no way I can squeeze it in right there. Never mind. Let's come over to this other board. Is this red marker hard to see? A little bit. It's okay. I'm kind of colorblind, so I have trouble with some of these colors, but if you guys can see it, I will use the red for the range like I did earlier. So for the range of T. Let's see, what was that again? That was the span of. And then I have to transform any basis for M2 of R that I want, right? So I pick my favorite basis for M2 of R. And I'm just gonna transform it. Let's pick the easiest basis that we know for M2 of R. Anybody wanna suggest one? 1, 0, 0, 0, okay, and then the next one? 0, 1, and then 0, 0, excellent. The next one, 0, 0, 1, 0, and the last one, T of 0, 0, 0, 1. It's just this big list. It's the span of all of those four things. Okay, so let me go to the next line, and what I'm gonna do now, guys, is I'm actually going to transform those four things. I'm gonna plug in 1, 0, 0, 0 into here. When I plug in 1, 0, 0, 0, I get 1, right? Just get an output of 1. And then when I plug in 0, 1, 0, 0 into the transformation, the output should give me 0. You're just adding the A and the D, putting a factor of 5 on the D. So the third one is also going to be 0, and the last one is actually going to be 5. So it's the span of those four numbers. And these are numbers because the W vector space is just the real numbers. Okay. Well, anybody think we should remove anything here? I would definitely not spend my $1,000 on those two zeros. So we will remove those. Anything else? Yeah, the 5 is just a scalar multiple of the 1, right? I would also remove that. And so my basis here, my basis would just be just 1 by itself. And that tells me that that is one dimensional. So my range is one dimensional. My range is one dimensional. So you see, guys, now I want to come back to the point I was making earlier. I did not actually check that these are Li earlier for the kernel. And you might have wondered, well, maybe I need to remove something here. Maybe it's not clear if I need to remove something, but we have our formula. The general rank nullity theorem. This is 4-dimensional. This one is clearly a 1 based on the work over there. There's only one basis vector. So I know that this number has to be a 3. And if I know that, then I know that these 3 must be a basis. I can't be removing anything. If I removed something from here, the dimension would drop below 3. And it doesn't if we trust this general rank nullity theorem. Yeah, exactly. That makes sense, guys? So far, so good? Let's do one more and then we'll take a little break. We'll get one more example into our chart here. And then I think we'll be good to go. So here is one more example. This is number 6. I'll probably do this one fairly quickly. This one is going to be T going from R2 over to P2 of R via, I'm going to take T of A comma B. I input 2 numbers A and B like that. And I'm going to output a quadratic polynomial, which will be this one right here, A plus the quantity B minus 2A x squared. Okay. So I'm just going to go over to my chart right now and put this one in there. T is going from R2 over to P2 of R, just so we have that ready to go in our little diagram here. And I'm going to find bases for the kernel and range one last time. Okay, so find bases for the kernel of T and the range of T. This is a lot of what Friday's homework is about. I think in the homework, in the problems in the book, when I wrote those problems, I was a little sloppy and I just said, find the kernel and the range. What I really want you to do on the homework for Friday is find a basis for the kernel and range, exactly what we're doing right now. And I think I put that in the assignment to do that because the instructions are a little bit unclear. But yeah, this is a standard type of problem for the homework that you're going to be doing for Friday's assignment. So again, we're just going to work out the kernel and the range. I guess we could start with the kernel again. It doesn't matter. If you feel like, oh, I'm really bad at the kernel, then that's fine. Do the range first. And as soon as you know what the dimension of the range is, you'll at least know what the dimension of your kernel is, if nothing else, right? So, but let's just stick with the kernel here. I'm going to take T of AB and I'm going to set it equal to 0. Obviously, I can put the formula in, so A plus the quantity B minus 2A x squared is being set equal to, and now I'm going to write the 0 as actually the 0 polynomial. So that would be 0 plus 0 x squared. And you literally just match these coefficients up then. That's how it's going to line up. So we get A equals 0, and then we get B minus 2A equals 0. And this is not rocket science, guys. We can solve that in our head pretty much. Just A is equal to B is equal to 0. And so my kernel of T would be what? The 0 vector, and I thank you for saying 0 vector. It's not just 0. I would actually write it as a 0 vector. So it would just be 0, 0. It should look like the form of whatever V looks like. So if it's R2, then these should have 2 slots. Okay. By the way, what is the dimension of that?
0.
How many basis vectors are you going to need to span this thing? I think this is something that also came up in my review session that I maybe didn't talk a lot about. There is actually no need to spend $1,000 here at all. There would be no basis to this whatsoever. So in fact, I would argue that on this example, the dimension of the kernel is actually 0. There is no basis that you would have to have for that. Okay, so that's actually just 0 dimensional. Let's do the range real quick. I'm gonna come back over here again, guys. It's so nice to know before I even take a breath, I already know what the dimension of the range is. What should the dimension of this range be?
2.
2, exactly. So we're expecting to see a 2-dimensional range. Let's check it out. So the range of T. The range of T, right? I'll just do this one right here really quick for you guys. We're just going to take the span of, and then I'm going to pick my favorite basis for R2. And if you're like me, probably your favorite basis is going to be 1, 0 and 0, 1. That's the standard basis for R2. So we're just going to plug in those things. So let's just see what we get when we actually evaluate T of 1, 0 and T of 0, 1. So if I put in 1 for A and 0 for B, this is going to be 1 minus 2x squared. So that comes in this first slot then, 1 minus 2x squared, and then comma. And then I have to do T of 0, 1. What's that going to be?
X.
Just x squared, right? Exactly. And again, normally you might look at this and say, oh, gee, I don't know if those are Li or not. But actually you do, for 2 reasons. One reason is they are not scalar multiples of each other. And the other reason is that you know that this number has to be a 2 in this table So if you have two vectors here, that must be your basis. Right, so this is actually the basis, and I just won't write it down again, I'll just put basis there. That has to be the basis. It's so powerful when you actually know what the dimension of the thing is that you're trying to figure out. Because then when the right number of vectors show up, you can feel pretty confident that you have a basis for it. Stick examples. People feeling pretty good with this? Pretty solid on it? Keep this little table handy. Did you save space for another column over here? I'm gonna put a header on this column now, and then we're gonna take a 10-minute break. The header is going to be, is T 1 to 1, so that's 1-1, onto both or neither. And after we take a 10-minute break, I'm gonna tell you what 1 to 1 means. I'm gonna tell you what onto means, and I'm gonna help you understand this 4-part multiple choice question. We're gonna figure out how to answer it real easily in just a few minutes. Let's take 10 minutes. Go ahead and stretch your legs and take a break.
Okay, I was making.
I must have been in a fog. Yeah, there's only 2.
Okay, for
There's only 2. Sorry about that.
No, no, you're good.
Did I confuse you about saying that there were 4 videos? There's only 2.
No.
Okay, good.
I had a question on the last column.
Yes.
Is that going into like surjective?
Yes. Yes, have you seen that?
Luis showed it to me yesterday. When we were
Who did?
Luis, SI.
Oh, okay.
Yeah.
Oh, nice. He was giving you a little preview.
He was giving us a little.
Oh, how nice. You okay, Keely?
Yeah, I'm good.
It's kind of quiet this morning.
Yeah.
It's a long night.
Yeah.
Okay. It happened.
Yeah.
Yeah.
Take a look at it. But it won't. Yeah. I feel like it was first. Take the last one. Take this one. Like the answer was like waffle about it. I remember having to do that. Like, what was it? Split them.
Anybody got any big plans for the coming weekend?
Halloween.
Oh, it's Halloween on Friday. Awesome. My favorite holiday. I
Really?
love, oh, I
Why is
love
it your favorite?
because I
You
love
like
the
scaring
candy.
children?
I know, I love the candy. Well, I love scaring big children.
The big.
Like whenever there's an exam on Halloween, it's like, ooh, I can really go nasty with it. No, it's. But, no, I buy those big bags of candy thinking, oh, I'll pass these out to the kids. Then I eat half of it myself.
Oh my god.
Yeah. I've been pretty good about staying on, I don't do drugs, I don't do alcohol, don't do any of that kind of stuff, but my I don't even like do the sugar drinks, but I do have, my weakness is I do like candy. So take me into a candy shop, I will have a wonderful time.
It's fun.
Yeah.
So hypothetically, if we brought you a ton of candy,
Ton of candy. You're gonna put a big smile on my face, except that I'll probably be like, oh no, I shouldn't be doing this.
what's your favorite candy?
Well, when my favorite candy for sure when I go hiking is gummy bears.
Oh, right.
Because they are easy to chew and they give you a quick sugar rush without choking. You don't
Right.
choke on them. But I don't know, that might be my overall, just anything's really loaded with sugar. I also like Nerds, so those Nerd gummy cluster things, I love those, but then I look at the sugar content in there. I'm like, I can eat like 2 of these little things, and that's all of the sugar I can have for the whole day.
Yeah.
What's that? They are loaded with sugar. You know, I know they are. Those gummy clusters. Oh, I love those things. Yeah, but they're just not that good for you.
I know, like, it's like a little somebody.
But see, that's why I like to go hiking also, because when I go hiking, I eat gummies. So I just.
Me and my siblings couldn't eat.
I wanted
to. I gotta have like a sugar rush, so I can do my thing, so I.
Nobody was like.
I enjoy the hike, but I also enjoy what I'm eating.
Yeah.
Oh, yeah, yeah.
Yeah, next year I did not.
I would
So,
idiot.
sad.
I love it. I love it. I love it. Even more than like. Not me.
Waiting on whatever somebody has to walk into this.
Oh, we got it.
Yeah, but I think that when you give me like.
Oh, whatever.
People were saying is that we're saying not just
Do these have really good offense? Your team might not be that sort of.
Yeah. I didn't think it was gonna be like easy, but I don't know. It's like, yeah, dude, I feel bad for the Toronto fans. It was like 3 a.m.
It was 3 a.m.
They stayed up watching just for a walk. I'd be so bad.
That's especially then you just keep going.
Yeah.
Really, really does. And the next two games after this, you're still gonna be here in LA. They'll be going back to Toronto. It's not as much.
Like my friend was like, it was like the 17th inning. She's like, I would have just left by now. Bro, if I was there. Like, why would you?
I take a shower. I take a shower, I got for bed.
Yeah.
2 full games. 18.
It was like 9.
Honestly, I'm crazy. I kind of wanted it to break the record. I wanted it.
Me too, bro. I wanted to keep
That would have been history.
Yeah.
Total history.
It still needed like another hour though of actual time. It's because there's no pitch clock. Back when it was broken.
I can't wait for the ABS system this year though, because this.
Are they actually
terrible. Yeah, this like terrible.
Holy. Like
Did you see
it's
that?
gonna be the only thing. I thought it was like you could challenge.
You're gonna challenge calls.
They're doing the minors.
That's so important.
It is,
Did you see
yeah.
how many missed calls he had on both sides?
There's-
Like he called the strikes like
On one
Right
side,
above,
yeah.
yeah, on one side. And then same thing on the inside, a lot of lefties and.
Yeah. What are the rules? I don't know what the rules are, like they use it in the minors.
These are the minors, so when you don't just, you don't bring with a call, you just.
You go like this.
Or you do that.
I think, and then they check it real quick. Like, they don't have to go anywhere, it's just like on the screen.
It's just on the screen. It just reverses whatever call. So it's kind of a.
Yeah, but like, what's the limit? Is there a limit on it? Can you just be like?
We'll see. That's gonna be a game changer. So many phone calls. The Jays got a little too creative. Like they extend their runner so.
You think?
Yeah, cause like, what inning was it? Like Vladdy was, that was a good play. But then they try to.
I started watching 11.
Give up a bunch of bombs. Bombs into the other system.
Yeah.
Ties up the game.
I started watching the 11th though, so.
They just had a lot of chances.
That's right, I noticed you came to the room.
As a visiting team, you really have to just.
A lot of traffic.
You already know that like as soon as they score.
But you just can't get up at like 5 and drive over here. Then you don't sleep.
Oh, yeah.
So he was like that. I mean, I know.
Yeah, that's the trouble, that's like, I have problems with that also as a hiker. I am a night owl type of.
They still have no
I
time to
was like,
sleep.
get up early.
That actually,
You go to
that's
bed
gonna be
early.
one of the
So you can just try to go
Yeah.
to bed early the night before, but I can never do that. I
Right.
mean, always just wound up till at least midnight
So like, what happened if you choose the hike like?
in the afternoon.
Yeah.
In the summertime, there'll be thunderstorms up in the mountains, so that's dangerous. And it's also hot. And it's just too funny and the radiation, I think, really takes a toll on you if you do that too much. So I like to start really early.
This is like entire. I'm just fine.
It's just
like.
getting out of bed is the hard part. Once I'm actually out on the trail,
Yeah.
oh, I'm glad I got up and it's fine. But yeah, it's just tough.
Yeah, no, I've seen the videos.
That's why a lot of times I'll actually buy trail. So that I don't feel.
I can't even like.
Get earlier to do the driving. I'm already literally camping right there in my car and it's happening, right? So I can sit as long as possible and then when I wake up, I go straight to the. That's what I do.
I mean,
But it's a struggle. I have probably slept in my car 30 nights this year. An entire month with all the hiking. I just did it this weekend.
Like in
Except it was a rough.
Like in the driver's seat or like the trunk?
No, I'm short enough, I can go across the back.
Oh.
Did you, so you ended up going to New Mexico?
I did, yeah, I ended up, deciding to do that. And the only thing bad about it was all the papers I had to grade. I took them all with me and I graded when I could, but I just didn't have that much time. Cause I was doing a fair bit of driving as well between the different places. But life goes fast. I didn't wanna like just
You don't stop.
not do something. I had to go take my. As soon as we get into November and December, it gets too dark and I don't like camping when there's that many hours of darkness.
Yeah.
So I will probably tone it down from here on out and just kind of lay low until March or so. Yeah,
Big Ben.
yeah,
Big Ben.
that's great. All right, well, I think we got everybody back. Maybe we can go ahead and kind of get back on track here again, guys. Any questions so far on anything I've said today? It's mostly just been reinforcing the video, but with this new insight. This new insight that I've really tried to highlight in the table, that there's a relationship between the kernel and the range. That is really amazing. The V and the W, the two vector spaces may have nothing to do with each other. One of them involves polynomials, another one involves matrices. Or one of them involves Rn and the other one involves polynomials, right? The two vector spaces are two completely different universes. And yet because we have this function between them, right, we can make statements relating subspaces within those two separate universes. I find that to be really a strong, this is what mathematicians thrive on, a strong connection that we're building through the use of a function. If anybody ever questioned how linear transformations could be important, right? They actually help us to understand both V and W better than we would have understood them as separate isolated spaces. So this is the whole idea of sort of tying these things together a little bit. I've got a few more definitions that I want to give you, and this is technically in the next little section here. Which is actually the last section of chapter 6. We're gonna finish chapter 6 today, guys. Can you believe it? Blink and you'll miss it. 6.4, the last section, I have a few definitions here that I want to spell out, and then we'll go back to our table and our examples and look at this a little bit more. So the first definition, I'm gonna make a little list of these here, is that if the kernel of T is just only the zero vector of V. So if this blue part in my picture over here is just the zero vector, if it is only the zero vector that gets transformed to zero and the rest of those black vectors are going somewhere else, then in this case, we say T is 1, 2, 1. And sometimes you'll see me write that as 1-1. So if the kernel is tiny, if it is totally trivial, then we're gonna say that T is 1 to 1. Secondly, if the range of T is equal to the entire W. So this would be the range of T, which is the red part. If the red part was actually filling the entire W, in this case, we say T is onto. So apparently some folks at the SI session yesterday got a little preview about this. 1-to-1 is sometimes called injective and onto is sometimes called surjective. So you'll hear those words, especially among mathematicians, but I will probably not use those words very often. I tend to just stick to 1-to-1 and onto. And then the third point is if T is both 1-to-1 and onto, if it's both, then we say that T is an isomorphism. Fancy word here. In this case, T is an isomorphism. And V and W, in this case, they are what are called isomorphic. So in that case, the two vector spaces are isomorphic to each other. Okay, so the T is called an isomorphism, and V and W are isomorphic, denoted, I'm going to add one more notation here. V with this twiddle equal sign. So we're going to put an equal sign from V to W and then put a little wavy line on top of it. When two vector spaces are isomorphic, we're going to write it like this. And it's not literally an equal sign, but the intention is that you think of them as basically structurally, they are the same. They are basically behaving the same way. I'm going to do some examples. I'll show you what I mean. Okay. So these are three definitions everybody's going to need to be learning. 1-to-1 just means the kernel is equal to 0. Onto just means that the range of T is the entire big universe of W. And then if we have both a 1-to-1 and onto transformation, we're going to call it an isomorphism. Right, okay, so let's go back to our summary of examples here. This chart that we've been building, I gave you a new column to add over here. And so I want to go through it and try to answer whether T is 1-to-1 or onto or both or neither. And of course, if it's both, that would mean it's an isomorphism. So let's take a look at that. Let's go through them one by one. Well, first of all, actually just looking at the table, can anybody tell me, are any of those transformations going to be 1-to-1? Do you see any of these
The bottom one.
6 transformations where the kernel is 0?
The bottom one.
the bottom one, right? The bottom one is definitely 1-to-1, right? Okay, so this one, I guess for the moment, well, actually, so let's just go through none of the others are. This is not, well, actually, this fourth one, we don't know. It depends on what the nullity is. If the nullity is 0, then yes, it would be 1-to-1. So I just have to put a question mark on number 4 because we don't know. It would depend on the matrix. So I'll just put depends on A. It depends on what A is, so we can't really answer that one. But you can see that on these others, number 1, number 2, number 3, and number 5, it's not 1-to-1. Because look at the kernel. The kernel is not 0-dimensional on any of those. On the last one, it is 1-to-1. Okay, so that's pretty easy. Now let's look at the onto part of the equation. For the onto part, we're going to be comparing the range of T with W. So guys, remember W is the vector space on the right side here. Okay, so like is the first one going to be onto? If the range is 1-dimensional, but the W is M2 of R, are they going to be equal? No. Right, because this is 4-dimensional, the range is only 1-dimensional. What about number 2? Is this one going to be onto? What's the dimension of M2 of R?
Oh, 4.
It's 4, right? There's only 2, so let's just start putting these in. Not onto, right? What about number 3? Is number 3 going to be onto?
Yeah.
The dimension of the range was 3, and we look at what W was, P2 of R, that's also 3-dimensional, so this one is onto. So that one is going to be onto. Number 4, it all depends on A. Let's go on to number 5. Is number 5 onto? The range is 1-dimensional, W is 1-dimensional, right? So that matches, so these are going to be, that one is going to be onto. What about number 6? Is if the dimension of the range here is 2 and my W is P2 of R, do those match? No, they are not matching, so this is not onto. That makes sense? I love how I can just do my 6 examples in like 1 minute. So this one is neither. Let's just circle the final answer. This one was neither. This one is neither. Number 3 was onto only. This one is all depends, question mark. And then this number 5 was also onto only. And number 6 was 1-to-1 only. So we got all those answers. And somehow I managed to do 6 examples and I don't have one single isomorphism up there. There's no example so far where we have both, right? But we're gonna get there. We're gonna get there, no worries. So far, so good?
Yeah.
Does this question sound kind of familiar to you as something from this class earlier? It was just on the exam, right? I give you a subset and I ask you, is it Li? Is it a spanning set? Is it both or is it neither? You remember that? If you remember that, then you maybe also remember that you can always crop off 2 wrong answers just immediately by comparing how many vectors you're given with the dimension of the vector space. Well, I'm about to show you that with this question, because I'm going to be giving you these questions, I'm going to be asking you, is T 1-to-1, onto, both, or neither? You can always cross off 2 of the wrong answers without even taking a breath. And then it's a maybe on the rest of it. So I'm going to put this down as some facts that would be really good to know. Okay, so there's going to be 3 of them here, guys, and this is going to look very familiar. This is going to remind you very much of what we did earlier. So this is some facts about 1-to-1 and onto transformations. The first one is, if the dimension of V is bigger than the dimension of W. If V is bigger than W, then T cannot be 1-to-1. It cannot be 1-to-1. And it might be onto. That would require further investigation to decide that. But it might be onto, but it's definitely not 1-to-1. Can I just briefly explain why it cannot be 1-to-1? Don't need to take notes on this, but basically it comes straight from here. If V is bigger than W, and then the range of T is actually within W, the red part is within W, that means the range of T is even smaller than W. So compared to the dimension of V, this number is less than that. Which means that this has to be at least 1. It's not 0, right? This cannot be 0 because V is bigger than the dimension of the range, strictly bigger, right? Strictly bigger, because that's what this says, strictly. This is not greater than or equal to, guys. This is strictly greater. If V is strictly greater than W, then this number will be strictly bigger than this one, meaning that you can't have a 0 over here. So you can't be 1-to-1. It might be onto, that would all depend on the specific transformation, and you'd have to investigate that. So we have probably some examples here, right? The first one, now that doesn't apply to the first one, or that one. This one, V is bigger than W, right? V is bigger than W, T cannot be 1-to-1. This one did turn out to be onto. Okay, let's do a second fact. Let's turn the story around, guys. If the dimension of V, guys, you are going to have to memorize this. I don't know how else to tell you. You just got to get this down. So if V is smaller than W, if we turn everything around, then T cannot be onto. It cannot be onto, and it might be 1-to-1. So emphasis on might. It's a maybe. You would have to check the kernel. You'd have to calculate the kernel and see, well, is the kernel equal to 0 or not? And it would depend on the problem that you're looking at. Okay? And then thirdly, third and final, is if the dimension of V is equal to the dimension of W, then, does anybody want to take a wild guess? Based on what we did before, yeah, T is going to be both or neither. T is both or neither, exactly. And so you would have to just check one of them and then the other one would come for free. So that's actually the reason we don't have any isomorphisms here is because I don't actually have any examples where the V and the W are the same size. Right? Here the W is bigger, here the W is bigger, here the V is bigger, here the V is bigger, and here the W is bigger. So I didn't actually give you an example yet where they are the same size. That might be part of the problem. Okay, let's see, where am I here? I'm just about got this all down. Is everybody good? Any questions so far? So if I give you a transformation and I ask you, is it 1-to-1, onto, both, or neither? The very first thing you should do is look at the dimension of V and the dimension of W, right? And if, depending on the comparison, you'll be in one of these three scenarios and you can cross off the 2 wrong answers immediately and kind of go from there. Okay, let's do another example then. Let me come back over here. I'm going to erase these definitions. Okay, so we've got to make sure you got them in your notes. We'll look at them if we need to. Let's try another example. Maybe we can just call this number 7. Just keep the example rolling. Let's define T from R2 to R2. So let's get an example where V and W are actually the same dimension. Right? And I'm going to do this via, now you already know, guys, this is the only one on the board where we're going from Rn to Rm. And that means that I'm gonna use a matrix to represent it. What size matrix do you think I'm gonna have for this problem?
2 by 2.
2 by 2, right? Because remember, Rn goes to Rm relates to a M by N matrix. So I'm gonna just define this via T of x equals Ax, where A is going to be the matrix 1, 2, and then 4, 8. And I'm gonna ask, is T 1-to-1 onto both or neither? Well, I mean, actually, I might as well just add a seventh line to my table. Can I put it up here? T goes from R2 to R2. Do you have another row to make in your notes? Let's try it. Let's just try it. Let's try it. So we'll actually fill out this whole table again. In the case of a matrix transformation, I'll just remind you guys that the kernel is just equal to the, what is it again? The null space of the matrix, and the range is equal to the column space, right? So we really just need to find the null space and column space of this matrix. And to do that, we hopefully, by the way, we already know, right? We already know we're crossing off, it's got to be both or neither. So I just cross off the 2 wrong answers immediately. But to figure this out, I actually do need to find the null space now. So if I look at the null space of A, this is for the kernel. So the kernel of T would just be coming from the null space of A. And to do that, remember that the procedure, hopefully you remember this, you augment the matrix with zeros. And I'm gonna hit it with one single ERO, which is just going to wipe out the bottom row, basically. Okay, so we just get the bottom row to go away because it's just a multiple of the first row. And if we line up some unknowns here like X and Y, people did a good job on this on the midterm overall, finding the null space of a matrix. So you just row reduce the matrix, set up your free variables. So in this case, Y is a free variable, I'll call it T. And then if I solve for X, using the first row of that matrix, X is just -2T. And so my vector, my basis, if I bust out that T, my basis is going to be -2 and 1. That's the basis for the kernel. And so what is that dimension? How many vectors do I have there in that basis? Just 1. So I'm going to put a 1 in my kernel column. Actually, if that's a 1, do we know what this other number will be already? What will it be? Also a 1. Right? And so 1 plus 1 adds up to 2. That's the way the formula, the general rank nullity theorem goes. And so is T going to be 1-to-1 onto both or neither based on those values? Neither, right? The kernel is not 0 and the range is not 2-dimensional here. So this one is also neither. While I'm working out the range, which I'm going to do now, I'm going to work out the range for this example. While I'm doing that, I want you to just ponder in your mind why this is turning out to be neither. I said something here, it kind of depends on A. So think about what it is about A that's kind of bad, that's making this turn out that we're getting something that's not an isomorphism. And while you think about that, I will work out the range over here. So for the range of T, this was just the call space of A. Ooh, this marker needs to go. The column space of A, actually, we can write down the basis immediately, right? Pardon? Somebody said it.
1-4.
1-4, yes, we just take the pivoted columns here and we translate back to the corresponding columns of the original matrix. So it would be 1 and 4, and sure enough, that has a dimension of 1. So we have one basis vector for the range as well. Okay. Yeah, so does anybody think they might know why this turned out to be neither? What would it take for the answer to have been both?
They were both LI, the matrix that we had.
If they were both, meaning both,
Both the vectors, like the 1 and the 2 for the 8.
The
They're
rows.
multiple, yeah.
if the rows of the matrix are Li, that's one way of saying it. Anybody want to give me another way of saying it?
No free variables.
No free variables, that's excellent. Does everybody want to give me another way of saying it? The rows of the matrix are Li. Actually, the columns would also need to be Li. They are not Li here. So what do you know? It's a square matrix. The columns, so what Trevor's saying is the rows would need to be Li. The columns would need to be Li. Give me another way of saying it. The determinant would be
0 or non-zero.
non-zero, right? Give me another way of saying it. Take your pick, guys. A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. This is called what theorem? The invertible matrix theorem. It must have to do with whether this is invertible or not. When the matrix is invertible, guys, that's a good thing. I always think of that as being a good thing. And in that case, the answer would have been both. You guys remember that for an invertible matrix, what's the null space? 0, right? For an invertible matrix, the null space is 0. Well, that would be the kernel being 0. That would be 1 to 1, right? And for an invertible matrix, the column space of an invertible matrix is the full Rn. And so that would be the range being equal to the full W, right? That would be onto. So this would be showing 1 to 1. This would be showing onto, and the two things together would give you an isomorphism. Let's write this down, guys, as a fact. That basically, if T goes from Rn to Rn via T of x equals A times x, then T is an isomorphism, meaning it's both 1 to 1 and onto if and only if A is invertible. That's the key point. So guys, good goes with good, right? So invertible is a good property for a matrix to have. And if we're using an invertible matrix to drive one of these matrix transformations, it's going to be an isomorphism, right? But if we use a matrix like this matrix is not invertible at all. You can see that for many reasons, right? In that case, everything is bad, right? It's bad, it's a bad matrix, and we get a neither for the correct answer here. It's neither. It's all fitting together so nicely. The theory just works so beautifully. Everything is just perfect. So I'm not even going to do another example of a matrix transformation. It's so simple. You just take your matrix and you figure out whether it's invertible or not, and that determines whether it's both or neither. Okay. Great. I want to do one last thing, guys, and then I think we're going to be good to go for this, which is I want to talk about like trying to actually construct an isomorphism. So far today, we still don't have even one on the board yet. 7 examples. We're 7 examples in, and we don't have a single isomorphism on the board. We do know that as long as A is invertible, and it's an n by n matrix, that would work. So we do have that example. Oops, I just erased the theorem there. I hope everybody wrote it down. But I want to try to construct isomorphisms with you. So just a quick note on this, and then we're gonna we're gonna call it a day. Right, so I'll just title this little brief conversation, constructing isomorphisms. And I'm just gonna go at this with a couple of examples here, first of all. So for a quick example of this, let's suppose I ask you to find an isomorphism T that would go from M2 of R to P3 of R. I actually want to construct one, I want to make one. First thing, I just want to quick sanity check. Is it even possible? We check our dimensions here. This is 4 dimensions. I just erased the facts, but the dimensions are 4 and 4, right? So if the dimensions, remember, if V was bigger than W, it couldn't be an isomorphism because it wouldn't be 1-to-1. If V was smaller than W, it couldn't be an isomorphism because it wouldn't be onto. The only way you even have a chance of having an isomorphism is when the V and the W match the dimensions. So I've set you up with one where it does, right? 4 dimensions here, 4 dimensions here. So there are lots of right answers to this question, but they're actually asking us to write down the T. Notice that on all of these other 7 examples, they gave us the T to begin with. So this is the first time today where I'm basically saying, I want you to write down the T. Let's see if we can do it. T is supposed to plug in a 2x2 matrix, so I'll go ahead and write that out, T of A, B, C, D. And what I need somebody to do is to give me an output. Now my output needs to be a cubic polynomial. I need somebody to take A, B, C, D here and give me an output over here that would be a cubic polynomial that you think has a good chance of being both 1-to-1 and onto. And anybody want to try it? Jose,
X cubed
excellent,
plus bx squared
excellent.
plus cx.
That seems so easy. It almost seems too easy, but that is beautiful. Guys, if you set this, if you ask yourself, what's the kernel? To find the kernel of this, you're going to set this equal to 0. Guys, the minute you set that equal to 0, you find out that A, B, C, and D all have to be 0, right? So if you do that, I'm not going to actually go through the verification here, but if you set this thing equal to 0, it implies, without even hardly having to do any work, it implies that all of your variables are zeros. In other words, that implies that your matrix is the 0 matrix. What's all this about? It's just showing you that the kernel is 0. So it is 1-to-1. Now, if I know that it's 1-to-1, do I need to stop and check if it's onto? If I know that this is 4 and this is 4, right? If I know the dimensions are the same, and as soon as I know that it is 1-to-1, then it must also be onto because it's both or neither in that case. This is a beautiful example. It's not the only one. It's not the only one that would have worked, but it's a great way of making an isomorphism. Just to make a quick little follow-up punctuation on this. When 2 vector spaces are isomorphic like this, which they are, right? So we're really saying here, guys, that M2 of R is isomorphic to P3 of R, right? Then what we're really saying is that they're more or less the same. They're more or less the same. Guys, if you added two matrices together, you could view that as just, well, take the corresponding polynomials and add those together. And the math will be the same in both contexts, right? Let's say that I hit my head on a rock and I forgot everything about matrices. I know nothing about matrices anymore. And you come along and you want to do a whole bunch, you have a whole page of, you give me a whole page of math that's a whole bunch of matrices, right? But somehow the part of my brain that knows about polynomials was fine. So I'm really good at polynomials. So what I could do is I could take your piece of paper that has all this algebra, all of this vector space stuff with matrices, and I could take every one of your matrices and recopy it as a polynomial. And I could do all of the algebra that you did using matrices. I could rewrite it just using polynomials. And at the end of the day, at the bottom of that paper, I would have discovered all of the same things that you discovered about matrices. I would have discovered them about the polynomials. Those two universes, the vectors might look different, right? Obviously, nobody is going to say that this matrix is the same as this polynomial, but the math works the same. The linear algebra, the addition, the scalar multiplication, the idea of a vector space is the same. It's just the way the vectors are being represented. I can give you another one. Guys. This is also isomorphic to R4. Because after all, I could take either one of these and associate it with, 4 slots that look like R4. And the math here would also be the same. So maybe I like working with polynomials, and Reed likes working with 2x2 matrices, and Dante likes working with vectors in R4. The three of us can all totally understand each other because we have these correspondences through these isomorphisms to do it. You see? So I'm super excited about that. There is a little bit of a bittersweetness to it for me though, which is that actually what I'm saying basically is that there are a lot less vector spaces out there, like substance-wise, there are a lot less vector spaces than you might think. These 3 vector spaces, other than how we actually write the vectors down, they basically are the same. And you could, if you chose, if you just want to work in Rn for the rest of your life, you pretty much can do that. Because if you talk to somebody else who likes to do polynomials or matrices, they can do that because they can just make these translations. It's just a dictionary, guys. These transformations, they are just a dictionary from matrix world to polynomial world to physics vectors world and whatever else you want to work in, if that makes any sense. There actually are some linear algebra classes out there that they never study polynomials. They never do matrices. They spend the entire semester just looking at Rn. And that's in some ways legitimate because every vector space is basically going to be isomorphic to some Rn. P7 of R. If you don't like working with 7-degree polynomials, fine. It's isomorphic to R8. And I bet you could write down the isomorphism, right? You just make your function, right? A x to the 7th plus b x to the 6th plus up to g, right? And you just send it over here to, up to h. And you just send it over here to a bunch of things with slots. And honestly, if you don't like polynomials, you can just translate it to this and do the math over here. I actually sometimes see students do this. And I pull out my red pen sometimes because it's supposed to be a matrix, but they wrote it as a vector with slots. But actually, in some ways, it's maybe a little bit more legitimate than I suggested to just sort of draw slots for everything. Because every vector space is going to be basically isomorphic, the same as one of these Rn's. And so you can actually do your whole linear algebra theory just in Rn and never have to touch anything else. We're not gonna do that. But that is actually possible to do. So, does this make sense? Any questions on this? Yeah, so there's some problems on the homework. Actually, this is for the next assignment for next Tuesday, where they actually ask you to construct an isomorphism from one vector space to another. Make it easy, guys. Make it a simple formula. Should be pretty good to go. Well, I am gonna do something absolutely unheard of. I'm gonna stop 2 minutes early. I'll let you guys go. Unless there's any questions, we are good for today. Thank you guys so much for being here. I'll see you next time. Extra, thank you.
I got photos of it.
Oh, you did? Okay, you don't want the physical one? Okay, fair enough.
Actually, can I get the physical one?
You can have it right now. I printed enough for everybody, so the only thing was, it was a. Oh, you fixed that typo already. Excellent, thank you. You're welcome.